Welcome to EET3329C Communication Systems. This is lecture number 3 at Valencia College for the fall semester of 2020. This is your lecturer, Dr. Wilfredo Rivas Torres, and today we will be talking about analysis and transmission of signals. Now, the lecture is divided in 3 portions. And the first portion that we will talk about is the Fourier transform theory, and then we'll talk about some transform of some useful functions. So far we have studied signals in terms of their frequency spectra and look at them in terms of their frequency responses. Now, essentially, we've been looking at the frequency domain. Now, the authors of our textbook started talking about different identities of the signals. And I had mentioned during lecture number 2 that this is really a different representation. So essentially, there is a time domain and there is a frequency domain. So if we look at the time domain here, right, this is what you would see on your oscilloscope, right? And this is what the signal looks to us sort of in real time, right? And what we learned with the Fourier series is that we can sort of decompose this signal in its different sinusoidal component or trigonometric components, right? And so we can have a fundamental, a second, and a third harmonic, let's say, right? Now I can take that same signal and instead of looking at it from the time domain, now we can look at it at a frequency domain. Again, we get different information or a different view of the same signal, right? And we can sort of derive other information that you can't see necessarily easily in the other domain, right? So, for example, in the frequency domain, if you notice, you can see kind of what the contribution from each one of these component is. But there's another curiosity here is if you notice, there's all this other thing that's happening down here. We clearly see the 3 components, right? But what is this other thing? That is actually noise, right? Notice that in the time domain, the noise is there, right? But in this signal, the noise is low enough that you cannot really detect it in the time domain. But in the frequency domain, it's clearly there, okay? And another aim that we were going to have is we want to look at signals that are no longer necessarily periodic, right? We so far talked about all these signals, we make them periodic. We want to extend what we know to the more general aperiodic kind of signals, okay? So the Fourier transform is the general tool that we use to deal with the more generic class of signals. Again, like the ones that are not necessarily periodic. So the Fourier transform, we normally the textbook and in our lectures will indicate the Fourier transform by the capital letter. So if we're talking about a signal g of t, we'll talk about the Fourier capital G of f, right? Another nomenclature that's commonly used is this f stands for Fourier, the Fourier of g of t, okay? And that is this integral from minus infinity to infinity of g of t, time domain signal, times e to the minus j 2 pi f of t, okay? And we also have the Fourier transform and the inverse Fourier transform. And like all inverse function, it sort of undoes what the direct function does, right? And we indicate that by f to the minus 1. So now we have a g of f, right? And we want to go back to look at what is the g of t. Now, that would indicate that the procedure that we have to use, that we have to use for that is, again, we do an integral of g of f e to the 2 pi j f t, okay? And it can be shown using a limiting process, that the Fourier transform can be generalized from the concept of the Fourier series that we studied in lecture number 2. Now, I'll put out the disclaimer now. In this lecture in the textbook, the authors do a lot of proofs. I will forego the proof in the sake for the sake of time of the lectures, but I encourage everyone to go look at the textbook and look at these proofs. They're mathematically quite fascinating to go through the process and understand that. Okay, and for this the proof, I would see textbook section 3.1. Okay, so let's talk about a few properties of the Fourier transform, right? The first property that we're going to talk about is the Fourier transform linearity or the superposition theorem. So if the Fourier transform is linear, it's a linear process. Therefore, if I have that g of 1 has a Fourier transform capital G of 1 and g of 2 of t has a Fourier transform g2 of f, then for all constants a1 and a2, if you add the two signals multiplied by the constants in the time domain, it's the same as adding them, right? And I want to determine the Fourier transform. It's the same as adding their two Fourier transforms multiplied by the same constants. You'll notice this double arrow and the rest of the lecture. That means the Fourier transform. So we're going from the time domain to the frequency domain through the Fourier transform. Okay. So what does the linearity um, transform, the linearity property of the Fourier transform tell us is that the linear combination of the signals in the time domain corresponds to the linear combination of the Fourier transforms in the frequency domain. And we can extend this to any finite number of terms. So you can have as many terms as you have in that you sum in the time domain, and you can have the same linear combinations in the frequency domain, as long as you can determine the uh, Fourier transform of all the gk's of t. Okay? Conjugate symmetry property. What this one says is if I were to have the conjugate of my function, if you remember what the conjugate of a complex number is, the conjugate is you just change the sign or negate the complex portion, right? In our case, if I were to take the Fourier transform and negate the complex, it's uh, like inverting the frequency, right? Or negating the frequency. Um, and then what we're saying is that to do minus the frequency is the same as doing the conjugate of the function, and this will be the Fourier transform. Which leads us to this other property, which is quite interesting. It's what that says that the magnitude of the Fourier transform of the minus f Fourier transform and the magnitude of equals that of the regular Fourier transform, and the phase of minus the Fourier frequency is minus the phase of the regular Fourier transform. The thing about this is you can say this for the amplitudes because it turns out the amplitude is an even function and the phase is an odd function. That's how come we can say this property here. In general, we apply this property only to real functions, non-complex functions. So if g of t were a complex function, this in general does not apply, so we don't apply it. A quick example, I want to run through this example with you guys, and I'll run through a few of them. I'm not going to run through all the examples in the chapter, so when you go through the chapter, you'll please study these examples. So we're going to look for the Fourier transform of e to the minus at times the unit step, right? So by definition, this would be the Fourier transform from minus infinity to plus infinity, but we notice that u of t only exists from t equals 0 and above. Below that, it equals 0. So we can immediately change the limits of integration from 0 to infinity because we know that less than 0 is going to be 0. Okay? Um, then we integrate this, right? Which ends up being minus a plus 2j pi f e to the same term. So how do we solve this? Because we have to evaluate it for 0 and infinity, right? Keep in mind that the magnitude of e to the minus j2 pi f t, the magnitude equals 1. Therefore, when t goes to infinity, right, this whole term goes to 0, okay? Because as t grows larger and larger, this number grows smaller, and it's being multiplied by pretty much 1, and it doesn't matter what this other term does because this tends to 0, right? And that applies as long as a is a number greater than 0 and or positive. So then the only term that we're left is evaluating this at 0. So if you evaluate this at 0, e to the whatever that is, because it's multiplied by t, becomes 1. And then that's how we get to this term. Okay, that's the Fourier transform. Um, Now, our author has this, or the author of the book, do this quite often. Did you guys notice we were working with 2 pi f, and then all of a sudden the answer has omega, right? Remember, omega is always going to be 2 pi f. So and I've seen this in different textbooks where they do this, right? Sometimes they're working with 2 pi f, then it's talking in terms of omega, and they bounce back and forth. And you can see throughout the problem, the authors here kind of do the same thing. Sometimes they're using omega, like in this case here, and then they go back to 2 pi f. Okay. Um, and then the rest of the problem, what they're trying to do is separate the magnitude and the phase, which I believe you guys can sort of follow that from the discussion. The rest of the example is plotting, uh, and the reason they separated the magnitude and the phase, so it's obviously so they can plot it. So if you look at the magnitude and the frequency domain, it has kind of this bell-shaped form, right? And then the phase has two asymptotes, and on the negative frequency side, it asymptotes pi over 2, and the positive frequency side is minus pi over 2, right? So as frequency goes to positive plus infinity, it approaches minus pi over 2, right? And again, it has this bell-shaped sort of shape, and notice that the maximum is 1 over a. Right? So this is what the spectra looks like. So if I were to create this waveform and look at it on a spectrum analyzer, I would kind of see something like this. Right? All right. Now, the Fourier transform, let's talk about the existence of Fourier transform, because it doesn't always exist. It depends, right? Like most things in life. So if you look at the prior example and you have a less than 0, that is negative, then when you try to do the integral, you'll notice that it doesn't converge. And when we say that something does not converge, what that means is there's no solution. It doesn't reach a solution, right? In our case, everything stay because there's going to be a growing exponential, right? The the a is going to be negative, so negative times negative gives you a positive number, so that exponential is going to continuously grow. Then things tend to go to infinity, and we said that's why we say it doesn't converge. It doesn't reach a solution. Okay, so not all signals are Fourier transformable. And in the book, again, they do talk about the existence of the Fourier transform is only assured if g of t satisfies the Dirichlet conditions. I urge you to look at the book. Again, I'm not going to spend the time to talk about Dirichlet conditions here. But I will tell you that in general practice, right, um, a signal will satisfy these conditions if the signal exists, right? If you have a signal that exists, doesn't go to infinity or doesn't blow up or something like that, um, or is not uh, the condition where it's zero everywhere. If you have a signal such as that, that you can see and you can measure, it does satisfy these conditions, the Dirichlet conditions. So the physical existence is a sufficient condition for the Fourier transform to exist. That's how come we can measure it on a spectrum analyzer, by the way. Okay, so let's talk about a few special functions. We've done this talk about special functions in lecture number 2. We have a couple more. So here's a special function. It's called a unit rectangular function. The notation is this, and if you haven't seen this Greek letter before, that's capital Pi. So pi of x for a rectangular pole is a rectangular pulse of unit height and unit width. So that would be this pulse here, which is defined like this, right? 1 for x less than or equal 1/2, and it's 0 everywhere else, right? And this is a unit rectangular pulse. And notice that the area under the curve here is actually 1, right? You could define it also in different ways. So we learned in prior lecture about the expansion of the functions, right? So if you have this function you divide x by tau, so you're expanding it by tau, right? Tau, it's just a number. And now you have that the function is much wider. Now the area under the curve is no longer uh, a 1 like it was in over here in part A of this figure. Okay. Um, by the way, for the rectangular pulse, whenever you expand the signal, that means you're expanding whatever this tau value is. That's how much you expanded the signal. That'll be the width of the signal. We also have another special function called the triangular function, and it's 1 minus 2 times the absolute value of x. Again, for x less than or equal to 1/2 and 0 everywhere else. And it just looks like a triangle. Okay, and observe again, we can expand the signal, right? And if you expand it by tau, that means that the base of the signal now across is going to be tau. Here's a special function. If you've taken the signal processing course, you probably have seen this function before. It's called the sinc function. And it's actually, the sinc function results in sine x over x. So whenever you see sine x over x, we call that the sinc function. Or this is the sine over argument. So the argument is the x, and if I divide by that argument, that's my sinc function. And this is kind of what it looks like. So as the sinc function goes further away from 0, it continues to become smaller and smaller and smaller. The amplitude of this sort of uh, and these are sinusoidal. Actually, we'll explain it on the next chart a lot better than I'm trying to do right now. So a few properties first, right? The sinc function is an even function of x. Um, sinc of x equals 0 when sine of x equals 0, which kind of makes sense because it's in the numerator, right? Except for x equals 0. So every time, right, that the sine, right, the sine of pi, for example, is 0, the sinc function becomes 0. Sine of 2 pi, 3 pi, you guys can kind of get the picture here. The same on the negative side, right? Except at 0, right? At 0, what happens is you have sine of 0 divided by 0. When you divide by 0, things go to infinity. Well, not really, because then you can apply L'Hopital's rule. For those of you who have forgotten, L'Hopital is down here on the right bottom right side of this chart. Um, so here's what I was trying to say at the end of the prior slide. The sinc function is actually an oscillating sine function, right, of period 2 pi, like all sines are, but it's also multiplied by a monotonically decreasing function, or 1 over x, the reciprocal of x, right? That's why it has this sort of shape. See, it continues to drop as it goes, as x goes to infinity. The sinc function um, it gets smaller and smaller and smaller. That the sine function starts getting smaller and smaller and smaller. Okay, so you can sort of draw these. They call them asymptotes, right? Um, some authors and then some places in the literature, you'll see SA of x. That also represents the sinc function. Um, Also, some authors and software packages, such as Octave, and by the way, MATLAB does the same thing, define sinc as sine pi x over pi x. So they put the pi in the equation. When you put pi in here, what happens is now the sinc function crosses at integer numbers, and that's why some authors like to define it this way, and that's why the software packages define it that way. Okay, so now instead of crossing uh, at, at integer numbers of pi, it actually crosses at just integer numbers. Okay. By the way, before I get too carried away, this function I actually did uh, do it through Octave, and when I use their function, you actually have to divide by pi in order to get this. Okay, because remember, it already assumes that it has the function is actually sine pi of x divided by pi x. If you don't divide by pi, then you don't get the original sinc function as defined on this slide. Hopefully that's not uh, confusing everybody. Right? Just all right. So let's do again. We learned a few special functions. Let's do a few Fourier transform. Let's start off with the unit pulse, right? Actually, it's not the unit pulse, it's the pulse expanded by tau. Okay, now if we go ahead and we try to do this integral, right, you'll notice that it's 0 everywhere else, so we immediately can change the limits of the integration to minus tau over 2 to tau over 2. When you do the integration, you realize that this portion here, if you go back to the Euler's identities, and you'll recognize that this is actually 2 sine pi f tau, right? And it's divided by 2 pi f, right? It's not exactly the sinc function, but if I multiply by tau and I both the numerator and the denominator, now I end up with tau sinc pi f tau. Okay, so therefore, um, the square pulse has a Fourier transform. Again, here's the author using omega, right? It will be omega tau over 2, or simply tau sinc pi f tau. And this is why we included the sinc function as one of our special functions, right? Because it actually is the Fourier transform of the pulse. Okay. And again, here is the same pulse, and the way we would do it um, in Octave would be, remember, you have to be careful to remember that it already has pi in it, right? So if you want to draw the Fourier transform, you have to remember that pi is already a factor there. So really all you have to do is the sinc function f tau, and you end up with this sort of graph for the representation of the Fourier transform of the pulse width, of a pulse of width tau, actually. Um, here's another interesting result, right? Remember the unit impulse, right? So um, let's figure out the Fourier transform of the unit impulse. Well, we're going to actually immediately, we recognize we're going to try to integrate from minus infinity to infinity, but because we have the impulse, right, we are going to use the sampling property of the impulse. So we only have to evaluate this at what? At t equals 0, right, this whole integral. So that is e to the minus j 2 pi f t of 0. So this whole thing becomes 1. So interesting, isn't it? The Fourier transform, right? The Fourier transform of um, of the impulse response ends up being 1. Quite an interesting result. Um, okay. Now we can actually even do the inverse. Let's do the inverse of, let's say that you have a Fourier transform that gave you impulse of f, right? What is the inverse Fourier transform? So we're going to go the other way around, which is a similar integral, except that now the exponential is positive, and we're going to integrate an f instead of integrating in the time domain. On using So when we do that, again, using the sampling property of the delta function here, you end up with e to the j0. And I know it says t, and it is t, right? But remember, t is a dummy variable here. What we're looking at to evaluate it is f. So it's 0. Again, this still ends up being 1. So if you have something with a power spectral density that looks as the impulse in the frequency domain, that leads to a 1 in the time domain. Now, the same thing here, right? Notice that when we plot this, if it's an impulse in the time domain, it's 1 everywhere in the frequency domain. If it's an impulse in the frequency domain, right? As if it's an impulse in the frequency domain, then it's 1 everywhere in time. What that tells us is that a DC value in time results in 0 frequency, and we know that DC, the frequency of DC is 0, and you only have one spectral component, which is the impulse, right? And by the way, the height of the impulse is going to be the same height as this DC value. The textbook doesn't say that, but that's what happens in reality. Okay. Okay. Again, now we want to find, here's another example. We want to find the inverse transform of a frequency shifted, right? We don't say a frequency delayed, we say a frequency shifted. This was in the time, we'll say a time delayed, right? But this is a frequency shifted, right? Now we're going to use, again, try to evaluate the inverse Fourier transform using the integral, right? And again, we evaluate this integral using the sampling property of the delta or the impulse function. And now we know that we only have to evaluate everything at f0, right? So it turns out that it ends up being e to the j 2 pi f0. And isn't that interesting, right? This is not a real function, right? This is actually a complex function, has a real and an imaginary part. How do we know? Well, again, Euler's identity, e to the j 2 pi f0 t actually ends up being cosine, which is the real part, plus j, this is the imaginary part, which is sine of the argument. Okay? Wouldn't it be interesting if you have an impulse on a single impulse on the frequency domain shifted somewhere away from 0, right? Shifted somewhere at some frequency f0, you end up with a complex signal in the time domain. Okay? All right? And we can do the same thing with the positive. Instead of shifting it uh, to the right with the minus f0, if you shift it to the left, then you end up with a still a complex signal in the time domain, but now you end up with a different phase, right? Because now that you end up with minus j sine of 2 pi. All right. Yet another example. Let's say now we want to find the Fourier transform of cosine 2 pi f0t, which is a real function, okay? This is a real function. And um, so here's our function. Oops, where did my marker go? Okay, there you go. So here's my function, right? Cosine of 2 pi f0t. Here's an identity that it's at the uh, in Appendix E6 of the book. Now, again, this comes all the way back to Euler's identity. That's all this is. Now, we can take equations 321a and 321b, which, by the way, are from the prior example. Okay, if you look at it, these two, right? So this guy and this guy are actually the same ones in this property right here. Okay, you'll notice here and you'll notice here. Okay, so this is what we're going to go ahead and um, um, that's what we're going to use, the two properties, because we already showed that you can linearly combine these, right? And it ends up being that cosine of 2 pi of 0t is 1/2, and then you have the two shifted frequencies, right? One to the right and the other one to the right and one to the left. Let me point to them correctly. This is the left shifted one. This is the right shifted one. So you end up that a cosine, right, has a Fourier transform, which is two impulses at plus and minus whatever the frequency of the cosine is. Okay. Now, in again, I did not spend a lot of time demonstrating and going very rigorously through all these integrals and even through the examples. The textbook does, and I hope you guys spend some time to go ahead and read those. Now, for the most part, in the rest of the course, I will refer back to this table, which is 22 different Fourier transform, and with this we cover a lot of ground. Notice that if you identify the Fourier transform, you can immediately perform the inverse Fourier transform, right? If you, let's say you identify that you have something that fits this expression 1a plus 2 pi f, then you immediately know that the inverse Fourier transform will be e to the minus at times the unit step. And there's a few of these, right? The same thing, the single unit step, again, we did not derive this, and but it's on this table. So here's what its Fourier transform would be. So if I gave you a unit step, you would know what the Fourier transform is. Okay, and we would pretty much use this table. And if you go to other textbooks, I'm sure you guys either in linear systems or in sometimes some of the signal processing courses, you study the Fourier transform as well, and even in some other electrical engineering courses, you would have find even tables much longer than this one with more entries. All right, so that is it for part one of this lecture. Part two, we will cover the properties of the Fourier transform, signal transmissions through a linear system, ideal versus practical filters. We'll see all that's about. And we will talk about signal distortion. Until next time.